Hi everyone. Today I'm gonna talk about the scintillation detectors presented by me, Dima Bashir Dasuki, submitted to Dr. Ali Kafarani in the High Resolution Gamma Spectroscopy course in spring 2021. Before starting with the scintillation detectors, I'm gonna talk about the detection system, which is classified into two types according to the method of operation. The first type is the pulse system type, where it is given one pulse per detected particle. The second type is the current type system, where we have average value resulting from detecting many particles. So the pulse type we have one pulse per particle. The current type system we have average for many particles. Here I want to note that if we can see in this table, for example, for the direct semiconductor detectors, the pulse duration is very low, it's a microsecond, and although the signal voltage is also very low. Starting with the pulse type system, as we said, one pulse per detected particle. So the pulse type system is built up of a source, detector, high voltage power supply, preamplifier, amplifier, single channel analyzer, scaler, timer, oscilloscope, and multi-channel analyzer. Now I'm gonna talk about each one alone. Starting with the detectors produce voltage signal related to the incident photon. Also, we have several types of pulse type detectors, such as the scintillation detector, which I will be talking about in this PowerPoint presentation, and the semiconductor detectors. The high voltage power supply, it provides a positive or negative voltage necessary for the operation of the detector. And here I want to note that the most of the detectors need positive high voltage. The preamplifier is necessary to minimize any source of noise that may change the signal. The purpose of the preamplifier is to provide an optimized coupling between the output of the detector and the rest of the detection system. So I have three main purposes of the preamplifier. Why I'm using this preamplifier? First, to amplify the small signals from detectors. Two, to shape the signals for remaining signal processing. Three is to match the impedance between detectors and signal chain. So why I'm using an amplifier? The main function of the amplifier is to amplify the pulses delivered from the preamplifier many times and making its stable form to be counted. So as we can see in this graph, the preamplifier output have many sharp peaks and it's not in a stable form, while the amplifier output it's countable and it have a stable form. So now I reach the multi-channel analyzer, MCA. It's used to convert the photon energy that result from the interaction in the detector into pulse with a certain height that can be recorded. It's divided into channel. Each has a width of voltage between certain limits of voltage V and V plus delta V. What does I mean by this? I mean that the lower limit of voltage is V, the upper limit of voltage is V plus delta V, and the width of the voltage is delta V. The distribution of pulses in that channel is an image of the distribution of energies of the photon that are deposited in the detector. Oscilloscope. Here we can see a photo of the oscilloscope. It is used to study the rapidly changing phenomena such as the sinusoidal voltage or the pulse of the counter. This phenomena is observed on the fluorescent screen. The horizontal axis is for the time and the vertical axis gives voltage. The single channel analyzer SCA, it's used to eliminate the electronic noise and to reject unwanted pulses. So in other words, when a pulse is amplified, the electronic noise that is always present in a circuit is also amplified. The scaler is a record of pulses. So for every pulse entering the scaler, a count of 1 is added to the previous total. Okay, so what do we have at the end? At the end of the counting period, the total number of pulses recorded will be displayed on this scaler. The timer is connected to the scaler, and its purpose is to start and stop the scaler at desired counting time intervals. So after finishing the structure of the pulse type system, I'm gonna sum up. So we have the preamplifier, which amplify and preserve information from detectors. The amplifier shape signals and provide additional amplifications if necessary for remainder of signal processing chain. And with this linear signal which I have from the amplifier, this signal can be processed to extract the radiation that interact in the detectors. So it's important to study the energy deposition in a detector. As we know, we have 4 main interaction of photon with matter. The first one is the photoelectric effect, the Rayleigh scattering, the Compton effect, and the Kerr production. I'm gonna talk briefly about the photoelectric effect by using this video. So as we can see, my target is calcium, and here I have a source of light. So now as I increase the intensity of this light, what will happen? More electrons will be released. If I lower this intensity, so as we can see, if I lower this intensity, we will still have electron released, but less. So as I increase the intensity of this light, more electron will be released. This is the photoelectric effect briefly. So number 2, the Rayleigh scattering. It happens when the incident photon is scattered by the atom and change its direction. So the target recoils to conserve its momentum before and after scattering. So as we can see here, we have the incident photon and the atom, and here we have the recoil atom and the scattered photon. So this process is happening to conserve the momentums before and after the scattering. The Compton effect, it happens when a single electron works as a target and where the recoil energy of the electron is larger than the binding energy of this electron. So as we can see, when the incident photon transfers a part of the electron, and a recoil electron is emitted after scattering. So as I change the scattering angle, the angle of the scattered photon will change too. So كل ما أنا غير the scattering angle, the angle of the scattered photon will be changed too. Here I want to note that the main idea of the Compton effect is that light is behaving as a particle. So now I will be talking about the last one, which is the Kerr production. In the Coulomb field bind of the nucleus or the electron, if the incident photon energy can be converted to the creation of electron and positron. So as we can see here, it's called Kerr production effect because we will have the creation of an electron and positron, as we can see in the video. So here I will have a summary about the deposit energy by photons. So in the photoelectric interaction, the photon gives all the energy to an inner electron and disappears. In the Compton scattering, only a fraction of the photon energy is given to an electron, and in the pair and triplet production, the kinetic energy of each particle is deposited in the detectors. So we will have the pair production or triplet production as we talked about right now. So now I'm gonna talk about the modes of energy deposition in the detectors before starting with the scintillation detector, which is my topic today. So we have two modes: the energy deposition by photons with energy less than 1 MeV, and with energy larger than 1 MeV. So starting with the energy less than 1 MeV, it can interact only through the photoelectric or the Compton effect. So if a photoelectric interaction takes place, the photon disappears and an electron appears with energy equals to E gamma plus EB, where EB is the binding energy of the electron. We have it, or it still exists, carrying the rest of the energy, and the energy of the electron is deposited in the detector. Finally, the scattered photons may or may be not interacting again inside the detector. The probability of the second interaction depends on the size of the counter, on the position of the first interaction, on the energy of the scattered photon, and on the material of which the detector is made. Unless the detector is infinite in size, there is always a chance that the scattered photon may escape, in which case a pulse will be formed with height proportional to an energy which is less than the energy of the incident photon. So as we can see here, we have a graph to be discussed. This graph is from the multi-channel. It shows the spectrum that registered on that channel. So first we have the full energy peak, which is the main peak, and then we have the Compton electron, which is responsible for the Compton continuum, and we have also the Compton edge, which is due since we have no detector with perfect energy resolution. So the measured spectrum looks like that, and sometimes the Compton interaction occurs very close to the surface of the detector or in the material of the protective cover surrounding of the detector. Now I'm gonna talk about the energy deposition by photons with energy higher than 1.022 MeV, where the pair and triplet production are possible in addition to the photoelectric effect and the Compton scattering. So what is happening here? The pair production will occur. What I mean by the pair production, that the photon will disappear and the electron-positron pair will be created. With energy of 0.5 MeV, there are several possibilities for the fate of these annihilation gammas. One, the energy of both annihilation gammas is deposited in the detectors. 2. Both annihilation photons escape. A pulse height is proportional to the energy. 3. One annihilation photon escape and a pulse height is proportional to the energy. So if a source emits only one gamma, the measured spectrum will certainly show full energy peak or Compton edge. Other peaks that may be observed are the backscattered peak, the single escape peak, and the double escape peak. The energy spectrum for various detector size: we have small detectors, very large detectors, and intermediate size detectors. Starting with the small detectors. In the small detector, the incident gamma ray energy is below the value at which Kerr production is significant. So the spectrum only from the combined effect of Compton scattering and the photoelectric absorption. While in the large or the very large detectors, all photons, no matter how complex their mode of interaction is, ultimately deposit all their energies in the detector. While for the intermediate size detectors, the photoelectric interaction give a rise to a full energy peak. The Compton scattering event can occur where the scattered photons escape the detector without further interaction, where this will give a rise to the Compton distribution. And also we will have the double escape peak will appear and the single escape peak will appear too, as we can see here in the graph below, in addition to the full energy peak. Now I'm gonna talk about my topic today, which is the scintillation detector. All the above mentioned ideas was to introduce this detector, this kind of detector. So what is the scintillation detector? It is a flash of light produced in a transparent material by the passage of a particle, which may be an electron, an alpha particle, an ion, or a high energy photon. So it is an instrument that is used for detecting and measuring ionizing radiation. It is made of scintillators that generates photons by excitation effect in response to incident radiation and detecting the resultant light pulse. So how does the scintillator detector works? The radiation strike the crystal. The photoelectron will be emitted by the scintillator. The electron move the cathode to anode through dynode. The electron pulse amplified and delivered. Finally, the electric pulse will be delivered to the PM tube. I'm gonna talk about how does it work in detail. So we have a scintillator material here, as we can see it, and we have a photomultiplier tube here, as we can see it. So we have this scintillator material when exposed to a nuclear radiation incident to the scintillator material. What happens that we will reach the photocathode and we will have the creation of a particle, so it will create light. The nuclear particle will enter the scintillator medium again, and electron in the material will absorb the energy from radiation or nuclear particle and jump to a higher band. So after that it will de-excite to a lower energy level, and it will release a form of energy. So the light photons will focus on the photocathode. As we can see here, this is the photocathode. So here the photoelectric effect will happen. The photoelectric effect that we talked about in the previous slides. Okay, so if the energy of the photon is enough, and the electron is released, and we will have the emission of the photoelectron. Where is the electron here? This is the primary electron. Okay, so the photoelectron enters the photomultiplier tube, and the purpose is to increase the photoelectron into very high value. So it leads to a significant part that can be recorded. How? As we can see here, these diodes are shaped like that because the electrons will be reflected to those targets. So what I want to say here, that each electron will release two other electrons. يعني here I have one electron, it will release two electrons. These two electrons will release four electrons. So each electron will release two other electrons. So imagine the big number of electrons will be released at the end. So these electrons are detected by some electronic setup here, the connector pins, and it is dependent on the number of primary photoelectrons. So the detected electrons here is dependent on the primary photoelectrons. So how does the scintillator detector work? When an ionizing particle passes into the scintillator material, atoms are ionized along a track. The photon from the scintillation strikes the photocathode and emits an electron which accelerated by a pulse and produce a voltage across the external resistance. This voltage is amplified and recorded by an electronic counters or electronic setup, as we mentioned the slide before. So here we have the scintillation detector apparatus. Here we have the high voltage power supply, the scintillation counter, the multi-channel analyzer, and finally we have a desktop computer to see our peaks and to collect our data. We have four types of the scintillator detectors. First of all, we have the CSI, which is for the detection of protons and alpha particles. We have the sodium iodide, containing a small amount of thallium, detection of gamma waves. We have the zinc sulfide, detector of the alpha particles. And we have the lithium iodide, which is used for the neutron detection. So finally, we're gonna talk about the application. Its application is for the personal and environmental monitoring for the radioactive contamination. 2 is for the national and homeland security. 3 for Weighbridge application. 4 for the nuclear security and nuclear plant safety. 5 for the medical imaging, and 6 for the scrap metal and contamination monitoring of nuclear waste. Thank you for listening. Hope you understood and enjoyed all the covered material, starting from the detection system, the pulse type system, the interaction and effects we have, and also the scintillation detector, how does it work, and its structure and its application. Hope you enjoyed and you understood all these topics. If you have any questions, please don't hesitate to ask.